Okay, so the stellar remnants. So we talked a little bit in passing about the different types of remnants of stars. But to be more specific, we have the white dwarfs, which are the remnants of stars that are less than about 8 or 10 times the mass of the sun. We have neutron stars, and we have black holes. Okay? Now, if we think about some material that's collapsing from the interstellar medium, some gas that's collapsing, we can think about what's going to happen to that in the distant future. So if it's really low, less than 1/10 of the mass of the sun, what we end up with is a failed star that we call a brown dwarf. Okay? And that remnant is quite small in mass, and it's about the radius of Jupiter or so. I don't know why I didn't fill out the density, but whoops. So, and what holds it up is something called electron degeneracy. And what that means is, it doesn't have to do with the fact that you could think, oh, electrons, they both have negative charge, and the same sort of charge repels. That's not how it works. It just has to do with the fact that electrons, because of their very nature, do not want to be in the same place, going at the same speed as another electron. Right? So it's sort of like, when you get on a bus, you don't want to sit next to someone. If there's an empty seat in another row, you'll take that seat rather than sit next to someone. The electrons don't want to be forced into the same state. So what that means is if you try to squeeze electrons into a smaller volume, their velocities will get larger. And that increase in velocity supplies a pressure to the gas, and we call that electron degeneracy pressure. Now, if the mass is a bit larger, somewhere between about half the mass of the sun and 1.4, we get something called a white dwarf. And the white dwarf, it's also held up by electron degeneracy. It's very similar to a brown dwarf. It's just, though, in this case, the star has evolved. It has turned hydrogen into helium, and for all the white dwarfs that are made in regular stellar evolution, it's also turned that helium into carbon, oxygen, maybe heavier elements still. And this object is about the radius of the Earth, and it's held up again by the electrons not wanting to be in the same state. As we go to larger masses, we have something called a neutron star, which is now held up not by electrons not wanting to be in the same state, but neutrons. So we call that neutron degeneracy. And then if the mass is even larger than maybe 3 times the mass of the sun, there's nothing that can hold it up. Now, I left out the column density. So the density of a white dwarf, if we figure it out, is about 10 million times that of water. 1 million to 10 million. So it's much more dense than the sun. For the neutron star, it's about 100 trillion times the density of water. So the neutron star's density is the same density as atomic nuclei. So you could imagine a neutron star is just a giant atomic nucleus where we've squeezed the entire mass of the sun into a ball that's 20 kilometers across. So the first thing to talk about are the white dwarfs. So the white dwarfs, you've seen them in your color magnitude diagram. They live down in the corner, the bottom left corner. They're hot, but they're faint, much fainter than a main sequence star. And that's because they're really small. So this is the person named Chandrasekhar who first thought in detail about white dwarfs. And we can see what their mass is along the bottom versus their radius. And you can see they're kind of strange. As the mass increases, the radius gets less and less, right? That's not the usual of what you think. You think more massive things are bigger, But for white dwarfs, as they get more massive, they actually get smaller and smaller and smaller. And the typical white dwarf is about 1/100th of the radius of the sun, which, like I said, is about the radius of the Earth. But the curve doesn't go on forever. It stops. You can see it stops just below 1.4 solar masses. So Chandrasekhar realized that although this electron degeneracy can hold up this object, there's a maximum mass that it can support, which is this 1.4 solar masses that we call the Chandrasekhar limit. And you remember this came up a lot, right? We could have a white dwarf plus another white dwarf if we have some accretion. If we have two white dwarfs who are like 0.7, 0.8 solar masses, if we smush them together, they go over the limit, or we take a white dwarf and accrete from its companion until it goes over the limit, and we get a type 1 supernova. And that's because it went over the limit. This same curve applies if we think of the core of the massive star. The core of the massive star is held up by this degeneracy pressure as well, because it can't have nuclear reactions. So as the core of the massive star, I always said it's around the size of the Earth, and this is why. So as it starts to build up the iron core, when it's 20% of the mass of the sun, it'll sit here, and as it grows, it shrinks, but eventually, if it gets above around 1.4 solar masses, that core cannot hold itself up against itself, right? Its radius is going all the way to 0. So the white dwarfs, they have a maximum mass, and this maximum mass is called the Chandrasekhar limit. And it's important for both types of supernova. The type 1, where we have a white dwarf accreting from its companion and going over that limit, and the type 2, where we're inside a star and it goes over that limit. So this isn't the first white dwarf to be discovered, but it's a white dwarf that's orbiting a star that we've all seen at night. So the brightest star in the night sky is Sirius. It's a star a bit more massive than the sun and pretty close to us. It's maybe twice the mass of the sun. And if you look at Sirius, what people noticed with Sirius is as it moved, it didn't move in a straight line, it wobbled, right? As if there was something orbiting it. And when they went to look at what was orbiting it, well, first of all, from the size of the wobble, they could guess that the mass of the thing that was orbiting Sirius was about a little more than half the mass of the sun. So you think, well, what does a star look like who's about half the mass of the sun? It's a red star. But then when they went to look at it, what did they see? They see this guy, who is blue. He's a blue star. So we can, by looking at that, we can go, well, if that star is about the same temperature as Sirius, but it's so much fainter, it must be a really, really small object, small radius. And just by comparing how bright one is to the other, you can conclude that that little guy radius is about 1/100th of the sun, right? So this star was a puzzle, like what is holding it up? And it turns out it's a white dwarf. This other picture shows it in the X-rays, where in fact the white dwarf is the brighter object in the X-rays. Right? So this is called Sirius B, because Sirius A is the bright star. What is it doing? Why isn't it going to the next page? So if we think about what's happening in our stellar evolution, we remember that the star becomes a red giant for the second time, and we call it an asymptotic giant branch star. And what it'll do is it starts to shed the mass on the outer layers of the star, all of the hydrogen, and in fact, or nearly all of the hydrogen, nearly all of the helium gets pushed out, and that will form a planetary nebula that we talked about. And in the middle of the planetary nebula will be a very, very hot core of the star, and that core, as it gradually cools, becomes a white dwarf. So here's the main sequence, and these planetary nebula stars live up here, and as they evolve and cool, they form a new sequence that's to blueward of the main sequence. So at a given temperature, they're much, much fainter. So for Sirius B would live around here, and Sirius A would be up there, and there's a factor of a huge amount in their luminosities. So here we think about, well, that's, if we look in our neighborhood, we see a lot of these white dwarfs around. They're hot stars that are quite faint. And they're relatively common because that's how every star who's less massive than about 8 times the mass of the sun will end up. It will end up as a white dwarf. Now, if we look at more massive stars, we remember that they have these supernova, and these supernova make neutron stars. So here is the center of a supernova remnant that's called the Crab supernova remnant. And we know it's a supernova remnant because people observed the supernova in the year 1054. And if we look in the center of the Crab, we see this little bright guy here, right in the middle. And that is the emission from a neutron star. So this neutron star is the Crab pulsar, and it was one of the first pulsars to be discovered. And I'll explain what a pulsar is versus a neutron star. All pulsars are neutron stars. But what it is there's a neutron star in there, and that neutron star spins around on its axis about 30 times a second. So 30 times a second, a pulse goes past us, right? And that pulse is in the radio generally, although the Crab, we see pulses in all sorts of energy ranges. So the basic idea of what's going on is you can think of it as a lighthouse, that the neutron star doesn't emit radiation in all directions, but in a particular direction, like a lighthouse does. And in a lighthouse, or at least in the olden days lighthouses, modern ones don't necessarily work this way, there's a big lens that rotates around, and what it means is only when the lens is pointing at you do you see the flash of light, and it rotates around again and again, and every time it rotates you'll get a flash of light. The same idea is for the neutron stars. So we have this schematic here. This is set up really like a lighthouse. So the neutron star is about 10 kilometers in radius. It usually has a strong magnetic field, meaning much stronger than we can make on Earth. And where the magnetic field comes out of the star, like on Earth, we have the north and south magnetic poles. On the neutron star, at the north and south magnetic poles, you have a beam of particles and radiation that are coming out. So when that beam crosses over the Earth, we'll see a flash or a pulse of radio waves. And every time it goes around, we'll get another pulse. For some neutron stars, we might see both the north and south pole. In fact, for the Crab, we do see the north and the south pole. So we would get 2 pulses that don't look the same every time it goes around. So this is the basic idea of how we see neutron stars. And we've discovered about 2,000 of them in this way. And they result from massive stars dying, will make the neutron star. So here we can see the pulsar leaving material behind it. So as it goes along through the gas of the interstellar medium, all the energy coming out of the pulsar excites the particles around it, and it can leave a trail, just like in our crab. All these particles, this is glowing electrons, really, that have been energized by the neutron star in the middle. We talked about these gamma ray bursts, and the gamma ray bursts, there were two ideas. One had to do with the star exploding, and one had to do with two neutron stars merging. And in this case, it was about noon in the UK, so 3 in the morning here. The gravitational wave detector in Washington and Louisiana detected the signature of two neutron stars merging, and about 2 seconds later, satellites orbiting the Earth, a particular one called Fermi, detected a gamma ray burst from the same direction. So this was really a huge vindication, because people had predicted that these two would be associated, but on top of that they had said this process of merging neutron stars will make lots of heavy elements all the way out on that table, and those heavy elements, as they decay radioactively, they will power not a full-blown supernova, but something they called a kilonova, which meant it was bright, but not really that bright. And in fact, all of this ended up coming true, right? So this was a prediction that with the first gravitational wave signature of neutron star merging, they also saw a gamma ray burst. They also saw the production of heavy elements such as iron, all in the same place. So it was pretty amazing. And that was last August. Now, this neutron star merger may have taken two neutron stars and created an object that was too massive to be a neutron star, like when I if I take two white dwarfs, it can go over the maximum limit. The maximum limit for a neutron star is maybe 2 or 3 solar masses. We don't know exactly. That's something we want to figure out. And it goes by the name the Oppenheimer-Volkoff limit. So Oppenheimer had a student called Volkoff. Volkoff was a professor at UBC, it turns out. And they were the first people to think about what is the structure of a neutron star. And that, like the Chandrasekhar limit, neutron stars have a maximum mass. And we don't know precisely what it is, but it's around 2 solar masses or 3 solar masses. So if you end up with a star whose core, for whatever reason, is more massive than that, or 2 neutron stars merging together, what you end up with is not a neutron star anymore, but what we end up getting is a black hole. So this is just showing a sort of an optical picture of a star in the constellation Cygnus, and this is Cygnus X1. So on the left is the reality. It lives in that little box, and it's a high-mass star that we see. And if we look at it in the X-rays, it's exceptionally bright. And we can estimate the mass that this high-mass star is orbiting another object who is more than 8 or 9 solar masses. So it can't be a neutron star anymore. And what we think is happening is the black hole accretes from the high-mass star, and as the material spirals into the black hole, it releases X-rays and other high-energy radiation. So here we're seeing, this is Cygnus X1, this is a black hole that's accreting, and this black hole was made in the death of a massive star, we think. So this was maybe the first evidence for a black hole that we had was from the X-rays from the black hole. But I want to give you a feeling for well, why is there general relativity? Like, why does it exist? And then also how it works, maybe in an intuitive way. And I know that's a really hard thing to get across to you, but we'll try, right? So in order to understand things like black holes, like in this picture, we have to think about how gravity works in a deep way. And more so than what we think of in just Newtonian physics. And here's a picture, right? So gravity basically has to do in the end with the property of space-time. And the first thing we have to do is say, well, what is space-time? And space-time wasn't something that Einstein invented. All of us deal with space-time all the time, right? Believe it or not. But we think of it as space and time. They're separate. So like, let's say I went to you, you need help with the tutorial, come to my office at Hennings, whatever, 417, and then I walk away. I wasn't very nice to you because I didn't give you all the information, right? We need a time. So whenever we want to make an event is more than a location. An event is, I'm having a party, it's my house, when is the party? So there's this concept of an event, which happens at a place and a time, or in space and in time. So we all know about space-time. The trick is in Newtonian physics, space and time weren't blended together like they have to be. And they have to be blended together. We see, and I'll go through why we realize that they aren't separate things. You can't talk about space without time. So in Newtonian physics, what you imagine space-time to be is there's a whole bunch of layers going through, and there's everything that's going on at this time throughout space, like the bottom piece of bread. And then there's a later time with everything going on in the cheese layer, and so on and so on. And they imagined space, you didn't really think of them as one concept. You thought of them combined as layers. So there's space at this moment, then space at the next moment, and space at the next moment, and so on. So if you were moving through time, it was quite a bit different than moving through space. Like if I move across space here, I just stay in the bread layer or the cheese layer, and if I move through time, I realize, oh, there's bread and there's cheese, right? It was quite a bit different. But a little more than 100 years ago, we had two things that were contradicting each other. One was this idea of Newton's how things move, and this concept of space-time that I talked about. And the other one was just how light worked, the laws of electrodynamics. And the key idea that happened is let's imagine that in your everyday life, if I'm in let's say a train, for example, and I'm throwing a ball to my colleague at the other end of the car, someone on the ground will, when I throw the ball towards the front of the train, someone who's not riding with the train will say the ball is going at the velocity of the train plus how fast I threw it. Right? It's the sum of those two. And that makes sense, I think. Right? I think to everybody that makes sense. But if instead of throwing a ball up and down the train, I decide to shoot a beam of light to my friend at the other end of the train, that beam of light, in fact, will go at the speed of light along the train. But to the person who's standing beside the train and the train's moving, it will also go at the speed of light. It doesn't go at the speed of light plus the speed of the train. No matter how fast you're going, the speed of light is the same, okay? Now, how do we know this? Because we measured it. It's not something that Einstein made up. People made measurements of how fast the speed of light is going in different directions. And one thing you have to keep in mind is the Earth is moving around the sun. So if we shoot light in the direction the Earth is going versus across, this is like going up and down the train, and this is going in a different, it's like measuring the speed of light for the person on the ground. And those two exactly equaled each other. So it got kind of complicated, and people said, oh, all sorts of weird stuff happens when it gets going almost at the speed of light. Things happen like how you add velocities together and other things. And it got really complicated. And what Einstein said is, let's forget about all these rules and forget about all we knew so far about Newtonian mechanics. And the basic idea was, instead of the speed of light being constant, being a property of light, it was just a property of space. But to make it work, you would have to think of something called space-time. You had to combine time in it, because speed is, in fact, how fast you move through space. So it's a combination of space and time together. So that became this thing called space-time. And we'll go through how it sort of worked. So the Newtonian idea was that everyone would look at that pile of grilled cheese sandwiches in the same way, right? That everyone could agree what's the same moment in time, and everyone would agree what is going forward in time. And because of this speed of light, you can't have both of those two things together. And I'll explain how. So in the Newtonian picture, if I had two events, let's say, that were separated by a given distance, like two things are going on, and let's say there's something going on here and something that's going on downtown. And here it goes on at 12 noon, and downtown it goes on at 1 o'clock, right? So there's some distance between the two, and there's a change in time, 1 hour. And in the Newtonian view, everyone would agree. They would say it's 1 hour apart in time and 3 kilometers in distance, for example. But, and we'll see how this works, in the new idea, if I were going past Vancouver really fast, or even not so fast, and I would see those two events happening, right? So something happened here and something happens there an hour later. If I'm moving through and I'm, let's say, going at half the speed of light, for example, because I can in my imagination, I wouldn't say that there was an hour between the events. I will say that there's maybe less time, maybe 45 minutes, and that they're not 3 kilometers apart, but maybe they're 2.5 kilometers apart. We won't agree on the distance between things, and we won't agree on the time between things. Now, that's something to get your head around. But there is something that we do agree on, which is sort of the sum of those two in a way. It's actually the difference. So there is something called an interval that everyone would agree on, which is combining the distance between events, like the 3 kilometers, and the time between them, 1 hour. You don't agree on those two numbers individually, but if you combine them in a special way, you'll agree. In fact, the combination is you take the distance squared and subtract the time difference squared times the speed of light. You don't have to remember that, but I'm just telling you that. So this was something called an interval. And then everything would work then. It meant now, because of this, and I'll show you a picture why this is the case, all the stuff with light would work just fine. Light would always go at precisely the speed of light. There would be weird things like, I said, different people would disagree on the amount of time things happen. And you might not believe that this is true, but it is. That is the way the world works. So a nice example, I can't give you everyday life examples because usually things don't go at nearly the speed of light in our everyday life. Usually, they don't. But one example is, and it's used, right? So when you cross the border into the United States, if you're in if you have a truck, they'll run you across the border a special way, and they scan what's in the truck. But there's nothing there, right? So how do they actually do this? So what they do is, below the pavement is a detector of particles called muons, which are like electrons, but they're heavy. And a muon, when it goes through the truck, if you have tons of uranium in there or something bad, it'll get stopped. So they'll know that you've got bad stuff in your truck. But the funny thing about a muon, it's a heavy electron, and it only exists for a tiny fraction of a second, like a millionth of a second. And in a millionth of a second, even going at the speed of light, a muon can only go 1,000 feet. Not very far. So if you think about it, well, where this truck is sitting there, where did the muons come from? They come from the sky. They're made in the upper atmosphere, but more than 1,000 feet away, right? So how does it actually work? So the muon gets made up there, and it's coming down at nearly the speed of light. From its point of view, it only lasts a millionth of a second before it becomes an electron. But from our point of view, since it's moving so fast, it can last 1,000 times longer or 100 times longer. So it reaches from the upper atmosphere, goes through the truck, detects that you have bananas or whatever, and then gets absorbed in the ground. And that's because, since it's going nearly the speed of light, time for it doesn't pass as fast as from our point of view. Okay? It's hard, right, to think of examples. But so this idea explained all the nuttiness about light and basically unified, grilled cheese into some sort of cheese bread. Where here, if I'm going through time or I'm going through space, it looks almost the same. There's cheese and there's bread, but there's cheese and bread everywhere. It's not like there's layers of cheese and bread. But let's make it a little bit more concrete what's going on. So if I make a sort of grid and I imagine drawing something on this grid, it'll have a certain length, right? Let's say I go from here to here and I draw a line. It'll have a given length. But let's imagine if I rotate the grid a little bit, right? And I measure it with a new grid that's slightly rotated. Will that thing still have the same length? It has to. If I measure it on that set of that graph paper or the other graph paper, it'll still have the same length, right? It's still, I can imagine, I wish I could draw a line on here. I guess I can. Let me draw a line so I can show you exactly what happened. It all died. Oh my goodness. All right. And I'm recording all of this. So now it's when I need my glasses, don't I? It's super small. What have I done? That is too small. Is it up there? You can read it. Lecture 11. Okay. That was just unfortunate. Is it going to do anything? There it is. And it's right there. So let's try to draw a line on here. I can draw a line. No, I can't. Annotate. So if I draw a line, there's the line. Oh, there it is, right? There's a line. I don't like it there. I'd like it in my graph paper. He's just showed up in a bad place. There it is. Okay, so here it is, right? So that line, if I look on the gray graph paper, that line is 1, 2, 3, 4, oh, that's 5, 6, 7, 8, 9.5 units long on the gray graph paper. And on the red graph paper, it's weird, right? So it goes across. We have to figure it out. Oh, that's the last time. It's not quitting again on me. So if I look on the red graph paper, I have to go, oh, it went across this way. 1, 2, 3, 4, 5, 6, 7, maybe that's 8, plus 3 in the other 2.5. But it looks like it's different length, but it's the same line. So you remember the rule. You go, I take the square on one direction of that length, add it to the square of the other, and take the square root. Right? Remember that? That was the Pythagorean theorem. So even though that I've rotated things, it has the same length. Like, we have two different frames of reference where we've rotated, and they both have the same length in both. Right? Does that make sense? So the distance between things, when I rotate, they stay the same. Okay? Oh, I'm just moving my line around. That's not very exciting. So when I rotate, it preserves the area of all those little boxes. It preserves the length of things. It also preserves the angles between things. If I draw a triangle on there, it's all fine. But would it preserve the speed of light by rotating? So let's think about, now we're going to think about time being one axis. We're kind of going to try to figure out something about space-time. We have time and we have position, and I draw something going the speed of light is always, I draw it at 45 degrees. And let's try to rotate this. And if I rotate this, you can see that that line has rotated. It's a different velocity now in the other. So they wouldn't agree on the speed of light. So someone who was in the red thing would say, oh, something going the speed of light does this. And the gray would be someone else, right? They don't agree. So thinking about how space-time works, it's a little different than just rotating in space, right? So for this person, light would pass through these events, and for this person, it would pass through those events, right? So it doesn't really work. So what Einstein came up with was something, it's a little weird, it's not exactly a rotation, it's something called a boost. So if you remember, when we rotated things, the thing that was preserved was this Pythagorean theorem thing. You would take the square along one length and the square of the other length, add them together, and that sum of the squares would always add up, right? And when you rotate, the length doesn't change. So here it is. So again, we're going at the speed of light. But what he came up with was this weird sort of thing. It doesn't rotate like you think. It kind of, everything squeezes in. So instead of being a grid that's perfectly square, if I look from one point of view, the grid is squished relative to the other. It's weird, I know, and it might upset you. But what it is just the same thing as that Pythagorean rule, except time is different. Time is a little different than space, right? I can't go to any time I want to. It would be lovely, but I can only go into the future, right? No matter what my intention is, I can walk to Burnaby, but I can't go to Burnaby yesterday, right? That's two different things. I can't go to yesterday, I can go to Burnaby. So time is a little different than space. And how does it work in this is, if you remember our little Pythagorean rule, you take the difference in one direction of space, square it, the difference in another direction of space, square it. You add those together, and that stays the same. What do you think it is for this? You take the difference in one direction of space, square it, minus the difference in time, square it. And that's what that picture shows. But let's think, this is kind of weird. What does this mean physically? So this axis, this thing is called T prime. And what that means is this is what someone would think of as space or time if they're moving relative to the other one, right? So this person, one person is stationary, let's say, and the red person is moving relative to the stationary person at maybe 1/10 of the speed of light because they move to the right a little bit, right? So you move one, let's say 1 square to the right for every 10 squares forward, right? So this guy's moving pretty fast relative to that guy. Now, but what's weird about it is, let's say I'm along here, this line, this gray line here, is a line of constant time for the person who's not moving, right? That's every event that's happening at one moment for that person. For the red person, every event that's happening at one moment is this line, the red line. I know it's going to hurt. It hurts. Sorry. But this is how the universe works, believe it or not. So this is weird because what it means is for someone, let's say someone's moving relative to someone else, one person could say, this happened, then that happened. A, then B. The person who's moving can see it in the opposite order, that B happened, then A. Yeah, sorry. That's the truth, right? Because you can look, right? So let's imagine that that this guy will make it even worse. Here's someone going really fast, maybe 60 or 80% of the speed of light. So let's think about something here. Let's see if we can make this happen. Let's do some drawings on it. So I'm going to put some events on the diagram, or at least I'm going to try without breaking the machine. So maybe I'll draw a line again. Do I have the line machine? So let's draw a line. Which one's line? Annotate. Let's draw a line. Okay. Oh, there's my line again. So let's try this. I'm going to try to draw a line between two different things. All right, I'm going to draw the line over here. Just for argument's sake, I'll draw it horizontally to make our life easy so we can figure it out. Like that. Woo! All right, now we'll make it big again, and then we can play around with it. All right, so that black line, right, those are two events. It connects two events. And for the guy who's not moving, they happened at the exact same time. The one on the left happened at the same time as the one on the right. Now, if we look at the red, the guy who's moving, from his point of view, the one on the left happens after the one on the right. Do people see that or not? Because look at his grid. Here's one time. This is a later time and a later time, right? So this lot is after that from his point of view. Yeah, it's giving you a headache, right? So this happens after that. Now, so what we wanted to do was to make it so they see things in the opposite order. So normally this one is after that to the red guy, and they're exactly at the same time for the black guy. All I have to do is, if I'm successful, oh, there we go. Now for the guy who's not moving, they see the thing on the left happen, then the thing on the right. For the person who's moving, they see the thing on the right, then the thing on the left. Right? Yes?
So then, relative to the gray guy's perspective,
yeah,
the other guy's going backwards in time.
No. If some guy went along the black line, Like if you went along the black line, it would look like you were going backwards in time, right? But the secret is, look at the black line. It's going really fast. If you wanted to go from point to go backwards in time, right, you would have to be going faster than the speed of light, because the speed of light is that blue diagonal. But yes, so that's why going faster than the speed of light is the same as going backwards in time. So like imagine if you could go from one end of that line to the other, right? From our point of view, if we're not moving, it would be fine. It went from one time to a time in the future, going from here to Burnaby, right? But to the person who's moving along, it looks like they went from here to yesterday. Sorry, right? Because the red guy, you start here on the left, and you end up backwards in time by 1 block, right? So if you go faster than the speed of light, you're going backwards in time, okay? So this creates a problem, right? So this is you don't want that to happen. I mean, it would be great if you could go backwards in time, but it created a problem, right? So Einstein said this, and so this kind of messed up all of our ideas of what space-time was like, and it's upsetting you that things can happen in different orders for different people, but get used to it if you want to. If not, you can just live life like this, right? Instead of like that, like, oh my God, this is the way the universe works. Okay. So here's why there's a problem with gravity, right? So Einstein came up with this. It had to do really with how things moved. So one aspect of Newtonian physics that we learned about, like that whole F equals ma thing, that effectively has to be revisited. But the second big thing that Newton came up with was this idea of gravity. Now gravity, we never asked this question, but we could. So I said that gravity pulls between me and you. But what happens if I'm moving really fast? Does it pull me towards where you are now? Or where were you in the past? Because it takes time for the gravity to get from you to me. We never asked that question. How long does it take gravity to get from A to B? And in Newtonian gravity, it takes no time at all. Happens instantaneously. So as I move around just now, my gravitational field, according to Newtonian physics, propagates throughout the universe instantaneously. So by moving, if someone could measure my gravity over at a nearby star, they would know it right now. They could wiggle, send me a message back. Like, for example, I could do a little message like this with like the lottery numbers, for example. And then that goes out to that nearby star. They put it on some spacecraft that's moving really fast that does the same thing. And guess what? The message with the lottery numbers would come back here yesterday when I could have done something about it. Does that make sense? And I'll show you how that works. Yes, because if I send something faster than the speed of light, it goes back in time, remember? So I could arrange that. Yeah, I'm sorry, it gives you a headache. So here's the idea. So let's say here's my job. I move around, and that propagates the message that I've moved along that green line. And but according to someone who's moving, that message actually goes backwards in time, right? So you can see the same thing. So the way to arrange it would be, I move around, it goes out there instantaneously. There's someone over there who's moving relative to me. They relay the message back by shaking something, and it'll come back to me again, going backwards in time. Yes?
Now, you may laugh at me, because this is not something thought of as, anyway. So this is life, in Interstellar where he sends a message back in time with the clock because gravity moved instantaneously, so he could send the message?
No, but when he's sending the message back in Interstellar,
Yeah.
he's inside like the singularity of the black hole as they imagined it.
Okay.
So guess what? Once you're there, all bets are
So it
off.
doesn't have to do with it. Okay.
It doesn't really have to do with this. The key is gravity doesn't do this. It doesn't travel instantaneously. Yeah.
We're seeing this just because you're putting the axes on top of each other. Like if I rotate, maybe the red guy.
I don't get to rotate. It's always this funny thing. So if I wanted to do this experiment, I didn't make this up to do the experiment. I'm just showing you. What I would do is I would send the message out that way to a guy who is moving fast, who would then, from his point of view, he has that gray thing, and I'm moving fast. So now if he sends the message back, I'm on the red part. So he gets the message at this moment. I'm moving fast. This moment is the same moment as right now. Boom. I shaked. He's over at a distant star. He's moving fast. He shakes. From my point of view, I'm now the red graph because I'm moving relative to him. The message comes back in time, and I get it before the lotto numbers were picked. So I'm a winner, guaranteed. Right? So that would be useful. Right? So someone moving relative to the mass would find that the field changes before the mass is moved. This is bad. I mean, it's bad because it leads to contradictions. If it actually happened, it would be good because we'd be making money. But it isn't. It doesn't work like that. So Einstein wanted to figure out how to fix up gravity, and he didn't want gravity to travel instantaneously. So do you know what he did? He essentially said, well, there is no gravity. That's how he solved the problem. He says there's a problem with gravity and with space-time. So what we think of gravity as a force, it's wrong. There is no gravity. That's how he solves the problem. He says, no, I don't want broccoli. There is no broccoli. I'm not going to eat it. It doesn't exist anymore. But how did he get rid of gravity? So if you remember, we talked about this special relativity was the idea that everyone who was moving relative to each other, if they did some experiments, they would always get the same answer, specifically like measuring the speed of light. But it was actually true for all experiments. You couldn't tell how fast you were moving by just making an experiment in a room. So what Einstein said to himself was, which makes it special, was things moving relative to each other at a velocity. To make it general, he says, if I'm accelerating, I say that, and I'm in a little room, there's no way to tell whether I'm accelerating or whether I'm feeling the force of gravity, right? So then he goes to say, well, then there is no gravity. Gravity is just equivalent to acceleration. And we'll flesh this all out. But here's just an idea, right? So if you're in an elevator and the elevator is accelerating downward, you feel lighter than normal, right? So you can turn the gravity, make the gravity decrease. Or if I'm accelerating upward, I can make the gravity increase. And if I cut the rope, I can make the gravity go away entirely, at least for a little while, until you slam on the bottom. So so the idea is let's think about gravity in a different way, that it's sort of like acceleration, right? So for example, if you're in one of those rides that spins, right, and you get pinned against the wall, you feel like there's a force pinning you against the wall, right? And you might say, that's not a real force because I'm spinning, right? And then we call that a fictitious force, right? But what Einstein said was, well, why can't gravity be a fictitious force? That we're actually just, when I feel gravity, it's because I'm accelerating against something, right? Okay, but what does that mean exactly? So here's another example. Like if I'm throwing a ball, and I mean, people see this in the space, like people in orbit, you throw the ball and it goes in a straight line. But if two of you decided to be falling, let's say not down a pit, but let's say you were jumped out of a plane, and instead of and before you kind of stopped going really fast, you could throw a ball back and forth, and you wouldn't have to arc the ball. Like normally to throw to you, I have to arc it up because of gravity. But if I'm falling, I just throw the ball straight to you, right? And that's what they're doing there. But from our point of view, who are not falling with them, I feel gravity. I see the ball taking a curved path, and I feel the gravity. Those two people don't feel the gravity, and the ball goes straight to them. Right? So when I know it's hurting. It's okay. So here's another example, which is more exotic, of them organizing their fruit bowl on the space station. Right? So you would say, you go, if you think about it one way, they're going in orbit around the Earth, and gravity is pulling them in a circle, and they're falling with the space station in the same circle, and everything sort of cancels out. But really, they're just the same people as going down the pit. They're freely falling in the gravitational field of the Earth, and because they're freely falling in that gravitational field, they don't feel the gravitational field, right? Okay. So how does Einstein solve the problem here? So what he said is essentially, how do things move from one place to the other? Newton's mechanics said, unless there's a force, they move in a straight line, right? No acceleration. They move in a straight line, unless there's a force. No one asked me when I said that, what is a straight line? Did anyone ask? No. So what Einstein said is, well, what is a straight line? So he wants to get rid of this gravitational force, and he says, well, the straight line is the shortest distance between 2 points, right? That makes sense. And it looks like a straight line as you're walking along it, in fact. But let's think about maybe on the surface of the Earth, the shortest distance between 2 points. When you go, it looks like you're going straight the whole way. But if you were to put it on a map, it would look curved, right? You've seen that, right? And that's because the surface of the Earth is curved, right? So the shortest distance on a curved surface, if you're walking it, it always looks like you're going straight. But if you come out of the surface, it looks curved. Do people know what I mean? So what he said is that what gravity does, what mass does, in fact, is it distorts space-time. So stuff doesn't go in how do you measure whether two things go in a straight line, for example, is I could take two objects and I set them going in this direction parallel to each other, and what will happen is they can get closer to each other or further away. That's how you could measure it. And it would look like there's a force drawing them together or pulling them apart. And I could call that force gravity, or I could just say it's the shape of the space-time. So why are they going around the Earth in this orbit? It's because that's the shortest path to get from this moment and this place to that moment and that place. And it's a curved path around the Earth. I know, it's a bit painful, but this is the basic idea. So what happens is this space-time, instead of being perfectly flat, what it is it's curved. And how do you measure the curve? It's just by throwing things around, right? Like if I were to take two sets of keys and throw them at the same velocity, but one a moment later, they'll take this curved path, and there'll be different curved paths, and that the space between them will change and then come back together. And that difference is measuring the curvature of the space-time, okay? Is this making sense? It's hard. That's okay. So here's how, this is actually the equation for general relativity, but I've written it in a very maybe simple way. So let's imagine I had this box, and I put a little rock on all the corners of that box, right? And it's just sitting there in space, 4 little rocks. And they're not moving apart just yet, but there's gravity around. So they could all of them could start falling towards the Earth, for example, right? Because they weren't moving, they'll start falling towards the Earth. Is that okay? Can people accept that? So with time, some of them will get a little bit closer to the Earth faster, and they're all getting pulled towards the center of the Earth. And if I look at the box a little later, the box will have changed its shape. It'll get long and narrow, pointing towards the Earth, for example. But what's interesting is if there's nothing in the box, let's say there's no mass in the box, before and after, the volume of the box stays the same. If you started them not moving relative to each other, they start freely falling in gravity, the box will change its shape, but the volume of the box will remain the same, right? No, this is like just the way it is. I can't derive it from like a rule. This is what nature does, okay? Now, if there's something in the box, like there's some mass in the box, the volume of the box will actually get smaller, like that. So what does that symbol mean? V is the volume of the box, and V double dot means how fast the box volume is changing with time twice, right? So it would be the volume of the box is 1 liter now, and that would mean it's decreasing, let's say, at 1 liter per second per second. The box is getting smaller, and it's getting smaller faster. That's what that means. It's an acceleration, right? So if I were to set this up, the box gets smaller, and it depends on what's in the box. So it's the mass of the stuff in the box, so the density times the volume. Plus there's this funny extra bit that has to do with the pressure of what's in the box. It has the size of the box, the volume, and then it has gravity. It has Newton's constant there. So that actually is all there is to general relativity, believe it or not. 2 things. One is space-time is curved, and things move through that space-time on a path that maximizes or minimizes the distance between one event and the other. So it's an extremal path. The shortest path is one way, or a line, if you want to think of it, right? And the second idea is that if you have mass, or any sort of energy, it distorts the space-time, but it does it in that exact way. That if I take a bunch of objects and let them go, they'll not only get close, the volume that is enclosed by these objects will decrease because of the mass inside. They'll get closer together. Which makes sense, because that's what gravity does. It brings things together. I know, that's a headache. So how do we know we're right? So this is like completely weird. It's not force is mass times mass over r squared. That was what we learned in Newton. Here I'm talking about a box. The box is getting smaller. There's some mass in the box, or there isn't a mass, and what's happening? It's a completely different way of looking at it. And in fact, if you write out the equations for something like a planet going around the sun, like here's Mercury, it changes the equations in the least. If you write out the equation and you would go, how could I change this equation in the most subtle way? And so the answer is almost the same, but the equation looks almost the same too, but it's a little bit different. Like everything looks almost the same, except there's one subtle difference that has to do now with the speed of light, right? That's what happens, right? It's a completely different way of looking at gravity, and it gives nearly the same answer, except when things are going really fast, right? And so, for example, one thing that we talked about already was in Newtonian physics, if something's in an orbit, it will take an elliptical orbit, and that ellipse will always be in the same place. In general relativity, the orbit will rotate with time and trace out a rosette. And this was already observed in Mercury's orbit, and it agreed with general relativity. The second thing that people realized at the time was that gravity could make light bend. And people sort of knew this before general relativity, but the little trick in general relativity versus Newtonian physics was that the light would bend twice as much. So the difference is a factor of 2. And they went out and measured it, and indeed, that's how it worked, right? The light does get bent by the gravity here of the sun. Shapiro delay. And what's interesting about the Shapiro delay, it's sort of like what I'm going to demonstrate here. What happened is when you send a beam of light into the gravitational field near the sun, for example, time goes slower, and also the space-time is curved. So the light takes longer to go across than you expect. So imagine if you had, 2 spacecraft that were a given distance apart, and then you stick the sun in the middle. It'll take longer for the radiation to pass between spacecraft A and spacecraft B because the sun's in the middle. And the gravity near the sun delays what's going on. Because one way of imagining it is, that the distance is a little bit longer than you expect because the space-time is curved. Also that the time passes at a different rate as you go down. Now, the bulk of what we experience as gravity, unlike a light beam goes at the speed of light. So when it travels through space-time, it samples the space part of space-time and the time part of space-time more or less equally. We don't go very fast through space, but we do go through time. So when what we experience as gravity is mainly the curvature in the time part of space-time. So I brought in this big ball to show you how that works, which, believe it or not, this big ball is like space-time. And I showed you some space-time diagrams, right, before. You're nodding your head like I didn't. They were very confusing. So space-time diagram basically had time pointing upwards and space pointing this way, right? And so if something goes slow, it's like that. And if something goes fast, it goes at a large angle with respect to time. And we don't go very fast. We kind of go more or less straight up. But here I've drawn it on a board. But space-time can be curved, hence my ball. So if we look at this ball, you could see, we can hold it this way, but I'm going to hold it this way. So these vertical lines that you see are time passing for someone not moving through space. You see that? What I mean? You see the vertical lines on the ball? Yes. And if I want to move through space, I go this way. Okay? So let's say I'm going to put some tape on, and that'll be the surface of the Earth, let's say. Well, if the ball doesn't roll around. So I'm going to put some tape. And then we'll look at this. So I'm just putting this here so we can see what's going on. So I'm marking a given line. You can see it's kind of hard. My tape gets all bunched up. Can anyone tell me why the tape is getting bunched up when I try to go around on a line? Why?
Because at the top of where your tape is smaller, but your tape is equal.
Yeah, so, but like in a very basic sense, it's because the surface is curved. So we run into a little problem with it getting bunched. But there it is. So this is me or you doing our business. Oh, wow, that one's kind of really bad, but that's okay. On the surface of the earth. And it's curved over here, you can see. Now, if I were to throw a ball up in the air, it comes back to the earth. So we can do that with the piece of tape. So this is up, and this is time passing. I'll do it like this. So let's throw a ball up. I'm going to throw the ball not so hard. So I've made it go, and I can do it with this piece of cord so you can make sure. So in space-time, it has to take the shortest path. So you can see if I pull the cord tight, it does that, right? So what is this showing, right? So here, I've thrown the ball up in the air, and this is time, this is space. It's not very large angle, so it's not going very fast. And as time progresses, it gets higher and higher. If you look at it this way, it gets above the surface of the earth. This is now time, and this is going up, goes above, and it automatically comes back to where back. No force. It's just because the ball is curved. Now, how would I make one that I threw harder up into the air? What would I do? I would make it go more vertical, right? To start. So let's do that. I'm going to start like that. Look at that one. I threw it at a faster velocity initially. It goes higher up before it starts coming down, and it spends longer in the air because this line along here is time. So the one that I threw slowly doesn't go so high, and it doesn't stay up in the air so long. The one that I threw fast goes like that. And the reason that this happens is just because up here, it's a shorter length to go a given time than down here. And that's what we call the gravitational time dilation, or just the curvature of the time part of space-time. Your brain is hurting. Now, this is worse than a black hole, right? So people are like, oh, like what would a space-time of a black hole be like? This curve represents, or this surface would be the space-time of a universe that was filled with matter of constant density. And I'll show you why it's worse than a black hole. And we'll learn a bit more about black hole. Black hole you can't get out of unless you can go faster than the speed of light. There's some limit. This thing you can never get out of. Watch. So let's say I decide I really want to get away from the surface of this Earth or whatever. So I'm going to throw the ball really, really hard. And in fact, I'm throwing it like that. So I've thrown it now, so this is horizontal. So I'm going much faster than the speed of light. In fact, I'm going infinitely fast, right? Because no time elapses, but I'm moving. But look, I come right back again. So this is, you can never get out. The gravity is even stronger than a black hole, right? Because you're always stuck here. And in fact, if the universe is what we call closed, meaning if its density is greater than, and we'll learn about it, this is the space-time, the time and space part of it. You can never get out of the universe if it's closed, clearly. You just come back to where you started, no matter how fast that you go. So maybe that helps you guys, but you can see here, just how curvature, a simple curvature, makes things that look a lot like me throwing a ball up in the air. Yeah?
If you get out of a black hole, you have to go faster than the speed of light.
Yeah.
Would you also not be going backwards in time?
Yeah, you can worry about that.
And so
Yes.
you would get out by going backwards in time.
Yeah, but you could also, yeah. There's all sorts of funny things. Like a black hole, eventually, they kind of destroy themselves. So do you ever actually fall in? That's a different question, right? Like if I were to throw you into a black hole, just for fun, just for giggles, I would see him getting closer and closer to the surface of the black hole, but I would never, ever, ever see you fall in. Because time goes more and more slowly for you as you approach the horizon.
Do I ever feel myself go in?
Well, that's the problem, right? So, naively, yes, if you just think of a black hole as an object that exists forever. But they don't. They don't exist forever. So after a very long time, the black hole will disappear. And that was Stephen Hawking's big discovery. So if I throw you into the black hole, I can't get convicted of murder because there is no murder. I can still see you there. Is he dead? No. Will he ever be dead? Probably not, because what will happen is in the distant future, the black hole will evaporate and you'll never actually go in the black hole, which is it's giving your head a headache. Like, if I cause someone to die in the future, am I guilty of murder? I don't think so. I mean, even if it's inevitable. I don't think so. I mean, there's a legal definition, right? So I don't know. But we're not going to throw anyone into black holes today. So the idea that space and time are curved and things take just the shortest paths, you can see how that causes things to appear like there's gravity. Now, for example, if I were to sit on the equator of this ball, on the equator, right near the equator, there is no gravity one way or another. And you can figure that out if you wanted to think about it. It's because on the equator, I can take this tape and put it all along the equator without it bunching up. And it's this bunching that is measuring the force of gravity at that part of the ball, believe it or not. Okay. What? Giving you that maybe was a little too far, I guess. So this is the Shapiro delay. What, you're thinking it's going to fall over? I don't know.
It's going into a black hole. It's never going to get there.
Maybe not. It's quite interesting. It's keeping you in suspense. I put that, oh, look, it's fine. You didn't know. I mean, it could have fallen over. Maybe it still can. I don't know. All right, so here we have this thing called the Shapiro delay, which was one of the things measured in the early 1970s. That was a test of what general relativity is about. And it turns out, this crazy thing that we think of general relativity, it is essentially has been verified in every situation that we have. So this is a lovely one where we have two neutron stars that are orbiting each other quite quickly. So each of them, they orbit in a few hours. So this is two objects about the mass of the sun, maybe 1 and a bit masses of the sun, orbiting each other sort of with the distance between the Earth and the moon. So pretty darn close, but they're each quite compact. So each one is about 20 kilometers across, but with 1.5 times the mass of the sun. But on top of that, nature has put a clock on each one for us. So we can do that experiment like with the Viking experiment, where we get a signal from one of the pulsars, for example, and it gets delayed by going in the space-time near the other pulsar. And that's one of these parameters here, two of these, called R and S. And that refers to this thing called the Shapiro delay. And general relativity predicts all of these different lines here. And they're lines that we actually talked about, most of them. We talked about this delay from going near an object in space-time, the gravity. This one has to do with the orbit of the two neutron stars. It's an ellipse, but the orientation of the ellipse changes in time. That's also predicted by general relativity. The one called PB dot, we'll talk more about that a little later. That's because as they orbit each other, they emit gravitational radiation that makes the orbit shrink. And the last one is called gamma, which is a weird thing. It has to do with the fact that when something's moving fast or in a gravitational field, time passes at a different rate, which we talked about. So general relativity gives all of these curves as a function of how massive each object is. And you can see their masses are a little bit more than the mass of the sun. And all of them agree in this tiny, tiny region here. So all of them, these different ways, these different general relativistic effects, all agree with each other and agree with the observations of this object. So this is work by Ingrid Stairs, who's in the next room, teaching the more mathy version of this course. So we were doing all of this introduction to think about what a black hole is, to give you a sense of this curvature of space-time. And let's just think of how a black hole might form. Basically, if we think of the core of a star, and if it's too massive, it cannot be stable as a neutron star. So it continues to collapse, and eventually the escape velocity from the surface exceeds the speed of light. And at that moment, what that means is since nothing can go faster than the speed of light, nothing can get out of that surface. Now, if we look at the poor astronaut, the astronaut is getting stretched and smushed like this. And that was just, remember, we talked about what gravity does. Like if there's nothing, if there's no mass in a region, what it can do is it can stretch and smush, but the volume. So this astronaut's volume is maintained, but he'll be stretched because at his feet, the gravity is stronger than at his head. So you get stretched, and that's called, they call it spaghettification. So that was what would happen to you as we threw you into the black hole. But depending on the mass of the black hole, when you get spaghettified, depends. So there are black holes in the universe whose masses are maybe 2 billion times that of the sun. So much more massive than this picture. There, you could go through the event horizon and you wouldn't notice a thing. And it would be too late to get you out. But if I threw you there, I would never see you pass. If I stayed far enough away, you'd still be you could be waving at me, right? So I'm falling in the event horizon. And what I would see from my point of view is he'd be like, I'm falling. And you'd just be frozen there on the surface for all eternity until the black hole annihilates itself. I can't go back and get you. Even though I can see you there, if I send a ship to save you, it's too late, believe it or not. Because one is the light coming from you to me, and the other is me sending something to catch you, and there isn't time enough for that. Yes?
Wouldn't he die from his perspective?
That's the problem, right? So this is why, if we want to get into the black hole more seriously, let's imagine the black hole exists forever. He would fall through that horizon, bye-bye, bye-bye, and a few hours later, from his point of view, maybe an hour later or 2 hours later, he would reach the singularity of the black hole. And then he would be shredded like this, probably well before then. So once he went through, he wouldn't know that he's past the point of no return. There's no way for you to know, at least according to regular classical general relativity. About an hour later, he would start feeling stretchy. And, that would be that. But I would never see him stretched because he would be just there. Quite happy. I'm going into a black hole. And we get like a snapshot. but that snapshot would get, as time progressed, would get more and more redshifted, like he would get even moving slower and slower and slower. Yes?
When reading about black hole,
Yeah.
the thing with this,
Poor guy.
this fellow said if he wants to be thrown into one,
Yeah.
because as he passed the event horizon, he would see time spread out in front of him.
Yeah, I could show you that. I don't know if I'll be able to show you that exactly. It's not strictly true for really any black hole, but so the point is when you go into the black hole, you have to think about what information you can receive from outside the black hole. And for a spinning black hole, there's a surface, which is maybe you could think it's pleasant, but it's not, where you see the entire history of the universe in a finite time, which is what he's explaining. But that's a bad thing, probably. Oh, okay. How? I could draw it in a diagram. I don't know if I have the diagram in here, but let's just continue through this, and then I'll try to draw a more complicated picture of what a black hole is in terms of what we call the causal structure, which means what you can see and what you can do and what you can do about and what you can't do about. Like, I can't save you, even though I can still see you forever. Okay, so here's what it looks like if you were standing on the surface shooting beams of light around. Just like we had on this surface, it was so curved that if I send something out really, really fast, it still comes back to the surface. On this star, as it gets closer and closer to be a black hole, what you find is most of the light that you send away gets bent back and hits the surface again. And when it actually becomes a black hole, even the light path that goes straight up doesn't manage to escape. And we're going to figure out when something becomes a black hole. So we basically can just use that concept of gravity, from gravity, called the escape velocity. And what we want to do is think about what is for a given mass, if I shrink that mass down to a given radius, when does the escape velocity equal the speed of light? So the formula for the escape velocity, we went over it a little bit, is just that the square of the velocity is twice times the mass times Newton's constant over r, the radius of the object. And basically, we're just wanting the escape velocity to be the speed of light. So if an object has a radius less than that number, and we'll calculate what it is, its escape velocity is greater than the speed of light. So if I take a given mass and I shove it in a radius r, smaller than this big R, it is a black hole, because light can't even escape. Okay? And we can put in numbers here to do the math. We know the mass of the sun. We figured that out earlier in the term. We know big G. We know the speed of light. And we get, for something the mass of the sun, it's 3 kilometers in radius. So if I take the mass of the sun, squeeze it down to a radius of 3 kilometers, it is a black hole. Now, if you remember, our neutron stars are about 1.5 times the mass of the sun or so. So for them, this critical radius is about 5 kilometers, right? The radius of a neutron star is about 10 or 11 kilometers. So they're almost there, but they're not. So for a neutron star, you have to worry about general relativity, but they are bigger than a black hole, right? They couldn't be smaller, because then they'd be a black hole and we wouldn't see them, but we do see them. Now, a couple things to keep in mind. Let's imagine that the mass is not the mass of the sun, but 1 billion times the mass of the sun. Then this radius is 1 billion times larger, 3 billion kilometers, which is pretty darn big. And we have black holes that mass in the universe. So there, if 3 billion kilometers is something like the size of Saturn's orbit, and people think of, material, it has to be really, really dense to form a black hole. But if we were to think about that, if I were to fill up all the region within Saturn's orbit with water, that would be enough mass to turn that region into a black hole. So it doesn't have to be that dense for it to happen. You just have to get enough mass in a small enough radius to get it to go. Yeah?
If it's past the neutron degeneracy,
Yeah.
the black hole, what's stopping it from getting smaller than that 3 kilometers?
Nothing.
So it just keeps getting smaller forever.
Yes! It collapses in on itself. And just, well, I mean, operationally, it doesn't have to happen forever. Eventually, it's like we just have a black hole. And it's inside it. And we can't know what's inside it because nothing gets out. Does that make sense? So what's in there that was maybe the question you were asking before. So I'm going to show you a more complicated thing, which is bound to give you a headache, but it answers your question. Now, if we had an object that's a star that isn't, well, it's not static, but let's say it's rotating, then you would expect the black hole to also have that rotation. And indeed, astrophysical black holes, we think they are rotating. And then things get more complicated, which is what you alluded to. So then everything has to fall in, but if we think about what goes on outside the black hole first, because that's where we can actually measure things, you have this funny region near the black hole called the ergosphere, where because the black hole is rotating, everything in that region has to go around with it. It's impossible for you not to go around with the black hole. You can't decide, like once you get in the region, no matter how hard you try, you're going to be spinning with the black hole. The whole space-time around there is spinning, and you have no choice but to go with the black hole. So that's this region here, the purplish region. And when you go closer to the black hole, you'll come upon another surface, which is the event horizon, beyond which you cannot return. Okay? But there's this intervening part where the black hole's effects are so strong, not that you can't escape, but you can't avoid going in the same direction as the black hole is spinning. So that's the outer horizon there. And then it had this other surface here, this inner horizon. And when you cross that inner horizon, you see the entire history of the universe from the point of view of the black hole play out in a finite amount of time. And that's what you were talking about. Okay? And then within this surface, we don't know, because that surface is kind of unstable. But if you were to just think about what would go on in the most naive sense, instead of all the mass collapsing to a point, it collapses to a ring. It's a ring of matter that effectively, it's like a ring of matter going around in a circle at the speed of light. It's pretty cool. And this is where people get, so I could draw a picture of this in terms that'll give to answer these questions. Let's see if I do it right. So we draw these diagrams called space-time, just like your usual space-time diagram, but for the black hole, right, like that. It's very loose here, and I'm drawing it very quickly. But this is the same sort of space-time diagram as we've been seeing, where we have time going up and going away from the black hole right and left. You do not have to write this down, but it's to show you an idea of what's going on. So someone who comes in, this is out here in our universe, here could be Earth, and we're near a black hole, and if I send someone in, they go in like this. Right? And that's them going into the black hole. I'm not going faster than the speed of light here. But now if you think about once I'm on this line here, if I go this is the outer event horizon, there's no way I can get back to the outside without going at greater than 45 degrees. So that's why I'm stuck in the hole. So once I'm in the hole, I'm stuck in the hole. I can't get out to this region because I'd have to go faster than the speed of light. This surface here lines up with this. So here, as I approach here, I can get radiation from the whole universe. This is the infinite future of our universe. So I can see the entire universe evolving before I get to that line. And if you look at the picture, there was one thing I drew, which are these things, which are the zigzaggy things. That's the actual singularity that you don't want to touch because you die, or if you get near it. But you can avoid it and go through and come out in another universe out here. So that's how a black hole can be a wormhole. Yeah, of course, giving you a headache, and that's fine. That's what we're supposed to do. No, but you don't have to do anything to get out. I just put you in at a given velocity. It's a straight line. You just go straight through. You don't need a rocket ship or anything. You just have to trust me that once you go in, you can come out somewhere else. There are problems with it, though.
Well, where I come out, there's no black hole, right? Because I'd have to.
Well, you come out of something.
But it's not a black hole because I'd have to be faster than the speed of light.
Yeah, it's so weird. It's like a white hole. It's the opposite of a black hole. Yes?
So if we were to do the space-time like a rubber sheet with this, right?
Yeah, I don't know how I would do it.
Going to the other universe where the thing you put on makes a hole in the sheet?
Yeah, you could think of that. Like there's this curve that pops out on another sheet.
Okay.
And because there's angular momentum, without angular momentum, these two things come together and you can't avoid the singularity. But since it's spinning, right, you can avoid hitting the singularity. But the one problem is once you're past this point, we don't really know what's going to go on here. Because when you go through here, you see, effectively, when you pass through here, all the light that ever comes into the black hole over the entire history of the universe will pass through you in a small amount of time. So you probably wouldn't survive that. But okay, so let's think about maybe more how we know there's black holes in the universe with the remaining time. So the main way that we see black holes up until September of 2015 is from them accreting from another object. So this is a picture of a black hole binary in our galaxy, or a schematic of it. So we have a star who's somewhat more massive than the sun, and it's losing mass to a black hole that's nearby, and the black hole just pulls it off using the gravity. And what we'll see is as the material spirals down towards the black hole, it gets stretched and squeezed by the gravity, and it heats up to millions of degrees. So that disk of material will glow in X-rays. So with the advent of X-ray astronomy, the first objects that were discovered in the early 1960s were a neutron star, two neutron stars accreting from a companion, and a black hole accreting from a companion. And that black hole is called Cygnus X1. And the reason why we thought it was a black hole, and we still think it was a black hole, is because it's in a binary, so we can estimate what the mass of the object is by looking at the other star, and we know it's like about 8 or 10 solar masses. So much larger than a neutron star could be. Okay? So if we look close, this is sort of schematic showing what's going on. This is not how it would look with your eye. I'll show you that in a second. You imagine that there's an event horizon. The material is moving up towards the event horizon. There's some point very close to the event horizon where it can't orbit anymore, so it just plunges in. So you can see that the accretion disk sort of stops near. somehow in a way that we don't understand, but it seems to be ubiquitous regardless of whether it's black holes or other objects accreting, we launch a jet of material that in the black hole case goes at nearly the speed of light. So we can see this jet coming out. And we'll see that a lot when we look at black holes in the centers of galaxies. But so the radiation from here, we get high energy radiation from this jet, meaning high energy X-rays, and also X-rays from the surface. Now, this is showing what it would look like if we ignored gravity's effect on light, because gravity bends light. To make this picture, the artist assumed that light goes in a straight line, so we could see it. But this is what it would look like for real. It's harder to tell, I guess. So here what we have is the accretion disk, and it gets bent around. The reason why we see it doesn't look flat, is because from behind the black hole, the light from, here's the black hole, let's say back here. Now this could be a black hole for us. Back here, there's some accretion disk, and if gravity, you can't see my hands, can you? I'm doing all sorts of horrible gestures, right? But I have my hands back here. This is the back side of the accretion disk. But because the gravity is so strong here, light from here where my hands are comes up and over, and you see it on the top. So that's what that's showing on the top, is the radiation from the part of the accretion disk on the far side of the black hole is over here. What this is, what do you think that line is? It looks like it's very near to the black region. What that is over here, right? You see the top of the accretion disk, right? But there's radiation coming from the bottom as well. It comes around you see the top of my hand. There's radiation from the bottom of my hand that comes around the hole and comes out here. So you see it, does that make sense? So that's what that little line is by the arrow, is you're looking at the bottom of the front side of the accretion disk, and so on, because it can go around many, many times, but the subsequent images are closer and closer to the event horizon. The event horizon isn't exactly that black region. That's what we call the shadow of the black hole. It can be bigger than the event horizon. Often it is. So that's where we don't get any radiation from. But you can see the black hole doesn't block light from behind it, because the light gets bent around the black hole, right? So it's not like the picture I showed you before where, it blocks. We can't see the other side, but we can. The light bends around. So the second way we know about black holes, that we're pretty sure that they exist, came from this experiment, which is, this is the one in Louisiana, because there's trees. There's one in Louisiana, and there's one in Hanford, Washington. The one in Washington is on a former, or maybe not former anymore, or maybe current place where they make nuclear weapons. So it's pretty, dodgy. So they have two of them, and there are not so many trees as far as I know. And that's not because of the nuclear weapons, but there you go. So what these experiments measure is, they don't measure light, they don't measure neutrinos, but they actually are measuring the curvature of space-time and how it changes in time. And basically what they do is, in that building there's a laser, and the laser is split in two, and it goes down one leg a few kilometers, I think it's 4 kilometers that way, and it goes down the other way 4 kilometers. And what they've done is they've arranged it so if the two, you have to realize, well, light is a wave, so it's going down like this as a wave, and they arrange the lengths of the legs so the light going down one way versus the other way goes exactly half a wavelength more. So what that means is when the light comes in, it comes in from the leg on the left up, and the leg on the right down, those two add up to nothing if the two legs are the normal length. Now what happens is a gravitational wave comes by. Remember, we talked about Shapiro delay. We talked about gravitational waves can actually make things move. If a gravitational wave comes by and let's say passes through here, what's going to happen is the light on that leg will take a little bit longer to do its route. So when it comes back, it won't be exactly the opposite. It'll be a little bit shifted, so they won't cancel out precisely. Does that make sense? And then we can measure how much light comes out at every moment. And they measure it thousands of times a second. Okay? Does that make sense? So what this experiment does is measure how long it takes light to go one way and compares it to the other way to a precision of, really tiny. I don't know, 10 to the minus 20 something. 23 maybe. So if one length ends up 10 to the minus 23 shorter than the other, they know it. Okay, does that make sense? Okay, so what they found back then in September was they looked, and what's measured on those curves is how much longer one leg is than the other. And you can see that there's a wiggle that they measured. And if you look at it, it has different data there. So the thing that's in yellow is what you expect from general relativity for the event. And what is in orange on the top one is what they actually measured. So you can see, and that's with the noise. So like if you were watching, like if this were on an oscilloscope, you would see this little scruff, and you'd look at the scruff with your eye. No big computer simulation or anything, and say something went on, and something did go on there. Now they observed it in Washington, and then down below they observed it in Louisiana. Now if you look at the two, is there something different between Washington and Louisiana? Can anyone tell me what's the difference between the two? Can you tell? I see a difference. They look almost the same, except there's a subtle difference. It's like, where's Waldo? What's different? What's different between Hanford and Livingston? Okay. Did they happen at the exact same time? He says yes. It's a trick question. No, look. So look when this guy is doing its final big wiggle here, right? And if I go straight up, this one's over there. Do you see? They're offset relative to each other, just by a little bit. Do you see that? There, right? This one is about here, right? And if I look at that same peak, it's there. Do you guys see it? All that is the time it took the gravitational wave to get from one telescope to the other. So it's exactly what you expected. They aren't exactly the same. They're just shifted by a tiny bit, thousandths of a second, which is how long it takes the gravitational wave to get from one to the other. So down here, they've taken the measurement from one instrument and the other and then shifted it by that tiny time difference, and you can see everything lines up. So what actually happened at this moment was gravitational waves from a pair of black holes. Here's a picture of what it might look like. I'll take off the lights. So this pair of black holes were born from stars that died maybe 10 billion years ago. And there were two black holes just orbiting each other since then until about 1.5 billion years ago. And 1.5 billion years ago, the two of them, all throughout time, these two black holes for billions of years were orbiting each other. And as they orbit, they were emitting gravitational radiation. And that made their orbit get smaller and smaller and smaller. And they went around faster and faster and faster until about 1.5 billion years ago, they finally got so close that they merged to form one black hole. Now, in that final moment, 1.5 billion years ago, they emitted tons of gravitational radiation. In that final moment, each of those black holes was about 30 times the mass of the sun. In that final moment, the last a tenth of a second of that orbit, they emitted about 3 or 4 solar masses of energy into gravitational radiation. And that gravitational radiation traveled across the universe for 1.5 billion years, and it washed across the Earth in the end of September 2015 and made these traces on the experiment. And what they did is, you can see, like I said, the difference in length is 10 to the minus 21. Right? So it's really tiny effect over the universe. So these guys, they merged together, they measured their masses, and everything agreed with what you expect from general relativity. So in a certain sense, I feel this is the first time we actually saw black holes, right? Because you saw them in their inherent nature, which is gravity. You see the gravitational radiation from these gravitational objects. So subsequently, they've observed from 3 or 4 other black hole binaries and from a neutron-star merger, which we talked about earlier. So it's still going on. Well, they're going to restart it